board. All right. So welcome everyone to our March webinar. My name is Colleen Graves, and I am the Curriculum and PD Coordinator for the National Center for Computer Science Education, which is the home of both CS Awesome and Mobile CSP. And we have lots of educators on the call tonight who have been on the forums and asking and requesting more information about physical computing. So this webinar is for you. We are going to spend the next about 85-90 minutes getting to hear from some awesome curriculum providers on their physical computing curricula and learn a little bit more about what physical computing is, because you may be here and thinking, what is it? Well, why do I need to know about it? So we are going to have some time to hear from some physical computing curriculum providers. So we have Makey, Microbit, Microsoft Make Code, and KISS Institute for Practical Robotics should also be here as well. And at the end, you will have some time to do some breakout rooms after they give their brief presentations to learn more and go into a breakout room with each of the providers and talk a little bit more about what they offer and ask more specific questions. I also want to introduce my colleague, Francisco. Are you there, Francisco?
Yes.
Francisco is our K-12 CS Pathways Program Manager at the National Center for Computer Science Education. And Francisco is going to lead us in just a brief overview of what physical computing is and help steer us in the direction of getting an understanding of what we're talking about here tonight. So I'm actually going to pass it over to Francisco.
Hello, my name is Francisco Cervantes. Thanks for joining us today. As Pauline said, I'm a program manager for K-12 Computer Science Pathways Project, and the goal of that project is to work with schools in building a computer science scope and sequence for their district. And so that includes multiple grades, multiple courses, units, and kind of implementation. Today I'll be talking, we'll just going to do a short kind of presentation or focus on physical computing. We'll start off with a couple definitions. And feel free to throw in some questions in the chat box or just jump in for me. We can kind of take those as we go. A couple of definitions that came across of physical computing. There's no, so yeah, the first one is an approach, defines physical computing as an approach to computer-human interaction design that starts by considering how humans express themselves physically. You may have not heard of that definition of physical computing. You're probably maybe familiar with the second one. Physical computing is a practice of building physical systems using hardware and software that interact with the world. And so there is I don't think a correct or wrong way. I think these are just two definitions. One highlights the relationship between hardware and software, how systems talk to each other. And the other definition, the first definition, it talks about a user design, notions of empathy, notions of connecting with the world, of learning how to express yourself. And so I think physical computing to me captures these two, if not other kind of aspects. And in the second slide, we'll go a little bit more into some of the specific computational concepts and practices that are associated with physical computing. But what I wanted to do is just kind of highlight that it's not about just making something. It's about how you treat someone else with the things that you make. And so sometimes that expression comes in either a touch, a visual representation, but multiple kind of interactions. Should we go next slide? And I think, Pauline, were you planning on covering this? Do you want me to follow up on this? No?
You can go ahead, Francisco.
Okay, I'll jump into this one. So why physical computing? Every programming environment, I think every programming platform has its own allowances, right? And so if I'm programming, an example of that is if I'm programming in Scratch, I may not be able to use a GPS coordinate with Scratch. I may not be able to do some sort of kind of networking across. And maybe I can create a global variable But each kind of programming platform has its own kind of allowances. And so if I'm programming, I guess for a mobile platform, I do want to use perhaps GPS, maybe have an accelerometer with that, right? So physical computing sometimes introduces these new topics, I guess, concepts in computing. The first one is sensing. The idea that data transforms it's received through an input, and then it's either kind of transformed into a yes or no, it's transformed into a numerical value. It can start off binary, you can produce a different sorts of variable. It really depends, right? And so that's what the power of sensing in physical computing introduces. And you might have seen some sensing blocks in programming environments like Scratch, but a lot of that sensing kind of happens on a visual kind of screen. So sensing allows for new things such as touch, and perhaps a light meters are an example of that. It also allows for networking, communication, devices being able to talk to each other, being able to communicate across. I think one of the most, I'm referencing Scratch a lot, so folks are probably familiar with Scratch, which is a programming platform in a community. But in Scratch, you're able to broadcast certain messages and across different sprites and projects, and sometimes. And so networking allows you to do that across different devices and be able to communicate, perhaps at a more sophisticated level than just a yes or no without any feedback. Actuation is another example of output, whether it's a motor turning, whether it's something connecting it, whether it's a servo motor, or any sort of a kind of output that you want to create. Sometimes you want to heat up something else, and you want to cool it down. It really depends on what that output means. And then power, of course, working right now with a school that's using microbit devices and other kind of devices as well. And one of the biggest kind of concerns is, will this run? I'm running out of battery, right? So sometimes physical computing introduces notions of energy. It's I think something that teachers forget what energy includes. We'll go to the next slide. Some of the benefits of physical computing I kind of listed here as an opportunity to, I think, not only explore new concepts, but also explore new practices such as making through crafting and doing. I think it also allows for, as we kind of talked about, networking devices and communication, as well as user engagement. And I think, to me, that's different parts of a computational thinking framework, where you're talking about concepts such as sensors and sensing, practices such as making and testing. Testing and debugging in physical computing is different. I've kind of noticed that testing and debugging when I'm making a Scratch project or any sort of project online is different than when you go testing and debugging with hardware. Right there, you run into limitations, as well as perspectives on who you're making for, what you're making, and what questions you're asking about the world. So some of the highlights of physical computing. We'll go to the next slide. So a lot of my work is in working with school districts in building their computer science scope and sequence. That means identifying good training, professional development for teachers to attend, evaluating good curriculum, and then really thinking of creating an implementation plan on how to make that work inside the classroom, as well as how it connects with students' experience from K through 12. And so I put two examples of computer science pathways. These are just examples, I think, of what I see, what I'm familiar kind of with across different, and so one is school district on the left, and then another box is school district on the right. I want to identify them, and really this is kind of a abstract or some things that I run in mind. And so I see a question on computational media, right? And so we can start there. The example on the left, it includes introduction to computational media. So sometimes that uses a P5 kind of visual representation. So computational media would be when you go to a concert and you see the display in the background, right? Flashing depending on the bass or a certain tune, right? Whoever created that whole expression in the background perhaps senses what the crowd is doing and it reacts to that. Sometimes it's based off the specific song. And so sometimes that is not just, sometimes it's perhaps just an image, but in other cases it turns into a visual representation that moves depending on on something defined by either the song or by that artist, right? So a lot of those folks who are creating those displays in their back are using P5. It is a really wonderful kind of opportunity to express yourself, and it's kind of one of the it's kind of not that kind of common, or it's not that talked about that much in industry. But we'll start off with their introduction to computational media and industrial arts class with Arduinos. And so we'll take a step back with elementary school on the left. I see Ruby codes and Scratch Junior as an opportunity for students to engage with programming environments, appreciate or kind of understand computers for the first time. In elementary school, you see a lot of, I sometimes run into it, the use of makey-makeys and Scratch. So kind of using Scratch Junior as a transition to a Scratch programming environment or a block-based programming environment. Makey-makey is awesome because it allows to explore the physical computing aspects of Scratch and kind of extend your projects. In middle school, it is an example of kind of online hackathons or virtual events, opportunities for students to really feel confident, to really build something perhaps for the first time if they didn't get a chance in elementary school, and share that with others. And at this kind of grade band, I do see a little bit more use of microbits, devices or kind of small processors without a display or with a small set of inputs and outputs. And so that's kind of what middle school space is used for, a lot of kind of projects, which leads into kind of high school and industrial arts class with Arduinos, which are a little bit more complex, a little bit more expensive, a little bit more powerful in that sense. On the right, I have an example of a scope and sequence in which it starts off again with Scratch, Scratch Junior. In some cases, as young kids being able to explore makey-makey, I think makey-makey really extends that elementary school and middle school grade bands depending on what a project is, and as well as high school. But I'm also seeing in elementary school the use of a little bit more heavy use of Scratch, Sphero, Dash, kind of physical or I wouldn't say physical computing devices, but they are kind of like, I like to call them packaged robots. I don't know if anybody has a better term for that, but these kind of packaged devices where you really can't see what's on the inside. It's all kind of packaged, but you're able to program them and manipulate them as you wish. In middle school, I see a lot of the creative computing curriculum used in Scratch, as well as kind of microbit and MakeCode devices. Really, middle school is, I think, a great opportunity to transition students from a block-based environment to physical computing and kind of other programming languages, and create links between one object-oriented programming language that's click and drag like Scratch to another object-oriented programming language that's also click and drag like MakeCode, but it allows for perhaps a text-based coding. And then in high school, exploring computer science and kind of other mobile CSP. So this is, I wanted to give you a sense of where physical computing devices, this isn't just there's plenty of other examples for that, for sequences and kind of those types of sequences. And we can go to the next slide. And so my previous position was working with the New York City Department of Education as Director of Computer Science Academics for middle school and high school portfolio. And so I worked with evaluating the performance of professional development providers for multiple teachers, and then also kind of giving feedback and identifying good curriculum, good training, and good experiences. And so on this slide, I put kind of this, you can consider this as your cheat list, your cheat sheet, right? Some good questions to ask professional development providers. What content is covered? And I think for that, the purpose of that is to be able to link between your previous programming experience that students have had or CS experience and future topics and content, right? So you want to be able to think about how they build on themselves, how you perhaps introduce new ways of thinking about those concepts. What makes a course different than other CS courses is always a great opportunity to identify what hooks or what makes it unique. Where might the CS course fit in your course sequence, right? So you're of course, looking for perhaps a great training, a great kind of hands-on activity, great curriculum. But I urge you to really think about what students' experience was before and where you want them to continue on, right? And of course, think about students who are having a CS experience for the first time, right? And so how can we reinforce and provide a great experience? Which teachers are best positioned to lead the course? Do you require prior CS experience is always important. Or what students are best positioned to take the course? And what types of project will students work on? I always ask for examples of students, right, of projects. I want to know what those are. Excuse me. And what do counselors market? How do counselors market the course and recruit students, as well as what infrastructure is needed, right? So what hardware do we need? What do we need to make this happen? As well as what are we going to be purchasing every year or so, right? So how much do these devices cost, and how much am I expected to spend every single year? Excuse me. And those are, so I think you should ask these questions to professional providers. You should ask these questions about curriculum. You should ask these questions to yourself, as well as what you're looking for, what would be a good fit, not only in your professional career, CS, computer science. And so not only your professional career, but also what within your scope and sequence. Yep. And those are a lot of kind of topics, a lot of questions that I covered from that period of time. And I think up next, we're going to hear for professional development providers on their training, as well as hopefully you can answer some of these questions and kind of paint a picture of what that looks like. I will pass it back to Colleen.
Yeah, thanks, Francisco. I definitely like the table that you had provided on the previous slide. That was nice because it aligned with a lot of the questions that we actually did receive from the teachers that registered tonight and may be here, and asking, how does this fit with these different levels? I might be in elementary or middle school, and what can I do? Which of the providers should I listen to, so to speak, to get their ideas? And then these questions are great. Again, they align with a lot of the questions that came in. So hopefully we'll be able to help answer these as the providers give their presentations. I did just have a brief question. So one, this is for Francisco. One of the common themes of the questions that came in that we got from the Zoom registration was from the context of integration. And so most of these questions are saying, how can I take what I'm learning about tonight and put it into my CS course? But is there anything that you would say to those who maybe are trying to do this in a science course or a math course rather than a standalone CS course?
Yeah. I'd say integration is not easy. I think start making something yourself, and then really think about how that fits into your curriculum. I think that you're best positioned to know how this content will integrate with, or how this hardware, how this activity will integrate with your curriculum. And I think the best way to get a sense of that is to really make that yourself. I think part of the skill that goes along with being is being able to match good training and good activities with where you're at, not only as your professional career, but also what meets the students. I think with that said, I've seen some I think great integrations with CS, and I think through art teachers. I think art teachers always have a great opportunity to see how this is being used and how this connects. I think vocabulary is always a great opportunity to integrate physical computing and really kind of and focus on that. Art and librarians are really one of my favorite folks to work with, because a lot of it is being inspired and by that tool. I think one of the suggestions that I would say is start small. Yes, go for it. If you want to build a huge Rube Goldberg machine and kind of think about how this is going to fit, it's awesome to be ambitious, but really try small, start small, build on that, and really share that with other teachers at your school for feedback, as well as how you can get some support. So I've seen integration in the sense of not just integrating with my own curriculum, but integrating it within my school. It's in my art teachers developing some sort of art project, and we can scan that in, and that will be part of this work. And so I think really leverage the professionals around you, leverage their feedback, because I think that's going to be really important as you build that unit. Yeah, and I don't know if that answers that.
Thanks, Francisco. And I would add, I see the chat going off, but I haven't had a chance to take a look at it. You're in a community tonight, right? For all of those who are here tonight, this is a community. This is a chance to ask questions and put your ideas into the chat. So feel free to do that. I'm going to go ahead and it's now time to dive a little bit deeper into some of our curriculum providers and PD providers that we have. So I would like to introduce Colleen Graves from Makey.
Hello. Oh, I was loud. Hey, everybody. I don't know, but I think you still have Francisco pinned just because. Oh, now I see myself. Okay. I mean, not that I want to see myself, but you know. Hello, everybody. I'm Colleen Graves, and I've been chatting here in the chat window, and I taught middle school and high school for 15 years and then have taught in elementary. I did actually taught in elementary, and then now I work for Makey full time, and I volunteer at local schools and try all my project ideas with real kids. And during coronavirus, I've had to do that virtually. So I'm trying to be there with you guys. So I'm doing what you're doing. So Makey is the invention kit for the 21st century. I do see it used a whole lot in elementary and middle school. When I taught high school, I still use this with high school kids and they still had fun, but wasn't using it as quite as much in the CS classes. It was more like as a librarian and maybe with art groups. So that's a really fun way to kind of incorporate us thinking about arts. So I did hear Francisco say, he was talking about that idea of the packaged and you can't really tell what something is. And so I think that's what makes Makey really fun, is that it's a creative computing kit that allows you to really think about the hardware that you need to build in order to make something happen when you do something with code. And just in case you guys didn't know, Zoom has this live transcript now, and I have it turned on. I'm going to have to turn it off because it's distracting me. But it's down there on the bottom where it says live transcript if you want to have your captions on. Can you go to the next slide? Oh, thank you. So this whole last year, I've spent creating courses for you that go from how, if you've never used Makey, my goal is to get you using it, get students just kind of understanding like what it is and understanding how to complete a circuit, and then understanding how to code a key press, because all Makey is a device that allows you to connect everyday stuff to your computer and control your computer. So it really is a great introduction to physical computing. But what I've seen is I want kids to do that, and I want them to go beyond the banana. I don't want them just plugging in and playing banana pianos. You've probably seen that. I want to see them to really start thinking about the science of materials and how they can come up with two different ways to complete a circuit. How can I put materials together, and what's the most interesting thing I can do? And then if I do that, what happens? So I usually like to end everything with an invention. So I'll show you that through the course of the 16 classes I've designed, the kids are going to end with inventing something. And so if you're thinking about the science of materials, that just means like I'm looking at how I can close two circuits. So this is a slap switch built by, I built this, but I built this off a design from John Lynch, excuse me. Mitten Brothers is his thing, and I'll put a link in there for you guys in a second. But this is a slap switch. And so the idea is that you've created a switch that you have to slap to close the circuit. So you're building the hardware part that goes to control your computer, right? And to me, having this as like the starter is something that just helps kids kind of understand like, oh, this is actually the same thing as the keyboard on my computer, except on my computer, these two things are only bridged when the top pad that has a conductive material comes down and closes that circuit. So I have an example here of me lighting an LED. I did think about the science of materials, like the way you can think about the different way materials can complete a circuit. So if you have an ice cube, or, and you have one alligator clip over here and one alligator clip over here, and your ice cube, as it slowly melts, it will complete the circuit. So that's just sort of thinking about how materials can change. Can you go to the next slide, Pauline? And Pauline, I love that your name sounds like my name. It makes me smile. So you can actually use Makey with all kinds of things, bananas, pie tins, anything conductive, and it uses it works like a key press and it looks like an old Nintendo controller because what it's controlling is the up arrow, the down arrow, the left arrow, and the right arrow on my computer, also space and click. And then on the back, you also have WASDFG and you have all your mouse movements. You can actually connect it to an iPad with an adapter because iPads have finally allowed external keyboards. Before, an iPad didn't really know what to do. But when you're coding with Scratch, it's actually just a little bit better to use letters and numbers instead of still the arrow keys, just because the iPads still get confused. But on a computer, code the arrow keys all you want. They know how to work. So I've created these 16 classes for you, and I'm just going to go really quick over what all of them are. And I had myself a timer and I forgot to do it. But anybody can use Makey Makey. Elementary teachers, secondary teachers, STEM coordinators, homeschool pods. And what I've really seen lately that's made me really excited, and I put a little bit in the chat about assistive technology, because when Francisco was talking, he said that we were thinking about physical computing and how it relates us to other humans. Just made me think about all the great work I've seen with occupational therapists and special education specialists using Makey Makey as assistive technology. So they're having their students create devices to help other students do something they couldn't do. And one thing I wanted to say that I thought was great about a high school connection that I saw, because Francisco also mentioned kind of working with others, is we had a group of high school teachers who had a math teacher. So the math teacher used Makey Makey, and he had his students design a cash register for the special education students that were running a breakfast cafe. So they're running a cafe, but they needed a cash register that was just simpler for them to use, that they could actually put in like the actual prices of things and not have to type all that. And it was really, really a cool idea. So you can get Makey Makey 1 by itself, $49.95, or you can get the STEM pack, which actually has 12 Makey Makeys and a bunch of accessories. And we really like to use that, see that as something for 24 students, because before coronavirus, we would always couple our kids and we'd have one hardware kid and one software kid. So one student who was creating the device and one student who was coding the device. And we can still do those things, right? We can still partner up, and I'll actually show you too. I created a virtual Makey Makey to help you look at that. So if we go to the next slide, I'll tell you about the, yeah, thank you. So the very first class is actually crafting a circuit because maybe students have never crafted a circuit. This lesson works great with, aligns great with 4th grade. And it's just actually doesn't even use a Makey Makey. But the reason we do it is because that is the same as using our computer key and pressing down you pressing down on the computer key is the same as if we were slapping a switch. So we're also looking at the way the battery creates a loop. And so I like to have students actually physically hold Makey Makey and see that they are the loop when they hold Earth and then they use their other hand to complete a circuit. They actually form a loop with their own arms and circles. So I like to do that. And then we look at what is conductive, because that's helping us think about that science of materials, like what kind of materials can I use? What is conductive? What is an insulator? And then we look at drawing an instrument so that we can actually just have students still playing, but they haven't actually gotten into computer science yet. And that's probably why you're seeing more Makey Makey in elementary, because we're getting kids started before they get into Scratch. Can you go to the next slide? And then we start looking at coding key presses. And the reason that I spend more time doing the others, because I really think some kids and some adults too, a lot of teachers, they don't really think about that these are controlling, that they're actually using these to control their arrow keys. And when they get into that part where we're looking at when this happens, do this, they start to get confused at how they're going to actually program those key presses. So it's kind of why we took a little slow dive into using Makey Makey a few times before we start coding our key presses. And after coding key presses, you can go into crafting and coding. I have interactive stories here, and I've also recently made this very beautiful interactive poster. And so this is a really simple way that people get involved, and they're not actually coding very much. They're really just coding that key press and thinking about how they can code different research that they've done. I also added Make Code Arcade because we tend to focus on Scratch, but you can actually use any programming language. And so you can use Make Code Arcade and you can build your own devices to use with that. And it's really fun. And I actually made a 2-player game on that one, and you get to learn how to remap the Makey. So if you remap your Makey, you actually end up changing all the inputs to whatever letter keys or number keys you want to use. And the last one in the beginner classwork is coding a poem generator. So it's very much just learning how to get started. And if you go to the next slide, I think I have all the classes here. I also spent some time because the elementary school teachers that I worked with really love to have these Google Slides with a whole lot of information on them. So I made these embeddable Google Slides for the first classes that you can actually put right into your Canvas or Schoology or whatever you're using, Google Classroom. And there's the virtual Makey right there. I think I could actually, because I'm not presenting. I would have to have remote access. But if Pauline were to click on the virtual Makey, she gave it to me. All right, I'll go to it now. So if I click on this Makey, it'll take me to Scratch where I've created a virtual Makey. And I did this because people were asking to have them and wanted to be able to use them with their students when they don't physically have the device. So an idea that I had was that we could all have a virtual Makey. So here's the virtual Makey. If you use Scratch, what you can do is actually, I'd have to be signed in and I'm not signed in, but when you click see inside, it feels so backwards. There's generally a backpack right here when you are signed in, and I'm not going to sign in right now just because I'm not me. But when you sign in, then you can just take the Makey and drag it like this into your backpack. And then your students can all have their own virtual Makey. So pretty fun. And then if they click on this, it'll take them to the piano. So they can play a human piano, or they can make a banana piano, and all the videos are set up there too. Now, the intermediate course goes a little bit further into thinking about how we're completing a circuit and looking at different ways. So designing switches and sensors by using things like binder clips. If I have this switch, this is a momentary switch that only works for the moment when I go through these. And when I'm using a binder switch, I can actually create what's called a maintained switch. So it's similar to the light switch, where this is now on and this will be on. And if this is connected to my Makey, the light's going to stay on until I pick up this. So it's kind of an interesting way to start teaching them engineering. Then they can hack a toy, they can design alarm systems. And it looks like I have a picture that I have wrong on here. I just see, but they can learn to craft tilt sensors. And my ultimate favorite, we'll go to the next one. Thank you, Helen. I'm glad that you're using all these with your third graders. That's really awesome. Can you go to the next slide, Pauline? Thanks. And then you start designing a life cycle project. You can actually look at, you can actually look at, I'm trying to talk and think because Chris mentioned something that reminded me. Also, here are those Google Slides, everybody. So you can have those. You can actually make an order. There's a secret code button. I call it the secret code button in Scratch. So there's an extension for Makey, and it'll put you all your Win key presses. And I've had teachers say, well, what's the point of that? And really the point of that is to help your students not try key presses that aren't on the Makey. And you're saying, who would do that? And I said, well, have you ever met a fifth grader? Because that's what they all tend to do. But the secret code button is really fun because it can follow the Konami code or any other code, but you actually code different sequences. So if I press up, right, down, and left in that order, then I want something to happen on my computer differently in Scratch. So that's how that code block works. And so if you did a life cycle project, you have to touch the right images in order to have a butterfly blossom, like so to have the life cycle complete. And then if I did a sequencing music with secret codes where you change the order to whatever you want, you can actually create a variable. So you learn a little bit more about coding by creating your own variables in that one. and have kids coding music. And in that one, I did my nice little hat tip to, I just forgot the name of the movie, but that's okay. It doesn't matter. Then my actually favorite class is actually this pixel art fingerprint project, because you're creating a coordinate plane, and then you're actually going to touch these different brass fasteners here to create shapes on your computer. So to me, this is a really fun way to look at creating. Chris just distracted me again, at creating shapes. So it's kind of like a geoboard, but you can actually create a physical geoboard that you can interact with here physically, but it's also going to do something digitally. So I think that's really, really fun. So you can tell this is a star shape, but you can also make a triangle or a parallelogram. And then the last class out of those 16 classes is the Invention Challenge, where students will design a math or literacy game for another student. So I actually got to do that last year before coronavirus. I got to take students, fifth grade students, and challenge them to create games for kindergartners. And the really amazing thing about that was they created games that are similar to what you see kindergarten teachers buying or parents of 6-year-olds buying. So my students made like these literacy games where they would touch numbers and then they would add numbers and everything would work in Scratch. So they're actually doing like real design work with this simple little invention kit. So it's pretty amazing. And that's why I have those courses going in that way. Now, right before I go, because I am up with my 10 minutes, Chris Coley made a good point about scrappy circuits. Here at Makey, we love scrappy circuits. And he has, Mike Carroll has a lot of great ideas on different ways to make really interesting connections. So spending some time building hardware out of scrappy stuff. So looking at things like recycling and office supplies and seeing how we can use that for inventing. So that's all you get for making. I think that's all my slides. Oh, of course. How could I forget? We are doing the summer PD with emphasis. We're actually doing it with scrappy circuits. So we're going to have 2 days of scrappy circuit building, along with going through the classes. So you'd have just enough time. So it's 5 full days to learn how to go from hacking recycled toys, creating alarms, and then creating your own invention. And so if you want to sign up for our PD, there's a link to that too. And Mike Carroll's going to be there with us and teach some scrappy circuits. So thanks.
Awesome. Thank you, Colleen. And if you have questions for Colleen, feel free to continue putting them in the chat. And you'll also do the breakout room opportunity at the end. If you want to speak with her one-on-one, you can feel free to jump into the Makey breakout room. Next up, we have the KISS Institute for Practical Robotics. And I believe we have Carol, Tim, and Steve are here.
Just Steve tonight.
Steve tonight. All right, I'm going to spotlight you. And I think we're good to go.
Perfect. So I apologize. Carol's actually teaching a JVC workshop right now, virtually to California, and Tim's teaching a aerial drone workshop right now. So as you guys can imagine, with COVID, our staff size has shrunk a little bit, but we've really expanded in the virtual space. So we're teaching workshops probably 3 or 4 a day right now, which is really awesome. So if you don't know about KISS Institute, we were started in 1994. This came out of MIT. Our founder did most of the prototyping on Sojourner, the other Mars rovers. He still does real-type rover work for NASA. He's currently on assignment at NSF as the project manager for the National Robot Initiative at NSF. So this organization was started by guys doing real autonomous robots a long time ago, back before coding was really cool, right? So the idea of our organization is we want to empower educators to impact students, and we do that with 3 main programs. We've got a junior bot program, which is mainly, it was designed mainly for elementary, but we're now even teaching it into some intro to engineering at the college level courses. And then our bot program, which is a competition program of autonomous robots. That's the one that started in '97. And then this year, because of COVID, we had to shift just like everybody else did. So we actually put up a virtual program that mirrored our other programs. And I'll show you a little bit about that. One thing I want you to notice about the picture, a lot of people think about robots and they think about competitions, right? They think, oh yeah, my kid's on the competition team. And oh yeah, so good, 10 kids out of 300 in the school. That's great. Great for those 10. But what about using a robot to teach something? Use it as a really cool manipulative. Now, my background, I taught 10 years middle school, a little over 10 years high school and undergraduate level. So mostly science and math, but I come from the education background and I also had robot competition teams. I did the big old first teams and all that. It was exciting, but the power to harness physical computing and take a moving thing and put it in front of kids it's just untapped. And it's good to see now. We see lots of people. We see Spheros and Dash and Dots and lots of people trying to do this. And I think it's a good thing because you get something moving in the kids' hands that they can control, and it has a whole lot of value. So a thing you notice about the kids, you notice they're all coding. I'm dead set against, the traditional one kid coding while 5 are sitting there looking. And you're like, oh my goodness, what I have to do then is this one kid codes and you do this and you have to sign all these different things. When in reality, what we want is we want to teach all the kids how to write code to control a physical system. So that's kind of what we're after. If you can go ahead and go to the next slide. So we've kind of got a 3-pronged attack on this. So basically what we have is we have reusable, classroom friendly hardware. So this is the robot side of things. And so for classroom friendly, I mean, this has to work without being connected to the internet, especially in elementary schools that have all kinds of firewalls and going in and out. Has to work in spite of that, if you will. So we designed hardware that doesn't need internet connection to work. We also designed it so that it can work with all kinds of devices, especially since COVID hit. If you can't work on a cell phone where we're at in Oklahoma, it has no value because a lot of kids have no internet service, but most of the kids do have cell service. So our hardware is designed, you can work it on a smartphone, on a Kindle, on a Chromebook, on an iPad, on a Windows XP machine if you want to. So that makes it much easier to actually do the program. And then the other thing we did is we made the robot such that multiple kids can use it simultaneously. So instead of the one kid plugging in and being connected to the robot and learning how to code while the others are doing who knows what, this case, 4 or 5 kids could be connected at the same time and writing their own different programs simultaneously. So one robot will serve, a lot of our schools in Oklahoma City are serving 30 kids in a classroom with 6 robots. And they'll do that for one class period. And the teacher across the hall will take them for the second half of the day and serve another 30 kids. And they share it up and down the hall. And within a week, they've reached almost 300 kids with 6 robots. So that part of the technology makes it easier to use in the classroom, if you will. And then the other piece we figured out was professional development. If you don't have professional development for the teachers, especially with what we do, because we're not doing graphical here, we're not doing Scratch, we're not doing Scratch Junior, we're not doing Blockly, we're doing text-based code. So we're doing everything in standard ANSI and or Python. And so if you're doing that, then you need a pretty strong professional development piece to do that. And it took us maybe a couple of years to develop that. I was kind of skeptical that it would work, but we've now trained, close to 4,000 teachers, elementary teachers, and they're writing code and teaching code with no problem. So this is very doable if the PD piece falls in line. And then the third big piece for us was the educational standards, because honestly, a lot of the robot programs, and they still are, they're extracurricular or they're add-ons to the school day. It's the robot team or it's the coding club after school for those who can attend. We wanted something that was in the class day that all kids could do, that any teacher, regardless of their background in coding, could also teach. So to do that, to get into a school, as you guys know, you've got to be aligned to standards. So we aligned to ISTE and CSTA, all the NGSS science standards we can hit, and then we did a full elementary alignment to Common Core Math. So there's math integration and math units that are in there. So that's kind of the 3-pronged attack. Next slide, please. So the Junior Bob Ball program, this was the piece, we developed this about 6 years ago. And the funny story about it, my wife at the time, Carol, was a STEM specialist at a OU think tank, University of Oklahoma at a think tank that went out and trained teachers around the state. I was running the BotBall program, which is a middle school, high school competition thing. And I said, I want to write some curriculum to help our middle school teachers teach some real coding, right? And they don't have any experience. They don't know how to do it. And there's really not much out there. Let me go about this. So I wrote some curriculum and I took it down to her and her team. And she came back and said, this is doable by third graders. Well, at the time, I didn't believe her. I almost laughed. I'm like, no way third graders can do this. They've got to be doing graphical. Everybody knows this. Oh, well, okay, let's try it. So we got a small grant from Best Buy Foundation and we put this in 12 schools. And we went in and we did professional development for the teachers, put it in with the kids, and did site visits to watch. And after about the first week of visiting the schools, I realized kids can write text-based code, no problem. In fact, they love writing text-based code. In fact, in elementary, they're learning syntax for writing every day. The teachers, this needs a period, this needs a capitalization, this needs an exclamation point. So what a great time to teach them syntax while they're already learning a language anyway. It was no problem. The only problem was getting the teachers and showing them how to actually teach this. So that was kind of the origin of the Junior BotBall program. It's now up, like you can see at the bottom, in about 1,500 schools, about 40,000 students. No experience required. It's aligned to standards. Everything is open-ended, inquiry-based, so there's no set solution. It's not a competition. It's basically set up around the paradigm of the teacher teaches the kids a few skills and then turns them loose with challenges or problems to solve. And how they solve the problem is up to the kids. So oftentimes what we see, instead of like a competition model, which is always the fastest, the best, the most, whatever, we train teachers to go in and say, okay, group of 5, here's what you have to solve with the robot. It has to go out and recycle this object. Okay, as a group of 5, you guys have to brainstorm 5 different ways to actually solve that. Okay, now that you brainstorm 5 different ways, break up and each one of you code one of the different ways and everybody share the results and let's see how it works. So the idea then is this is collaborative problem solving using code and a physical robot to solve the problem. This is not to go out there and score the most points to win a trophy. And with that, we've seen large participation by girls, large acceptance by teachers in the classroom because it's easy to manage. Once the kids know their robot and know what the task they're on or where they're working, the curriculum, there's actually 24 modules in it. It's all self-paced. So one group may be a little bit ahead, fine. You can just teach them another skill and on to the next activity. So how do we see this thing playing out? When we started, it was the same old story with robots. It was gifted. How you have to be brilliant to be a programmer. All those stereotypes started out gifted and talented, extracurricular robot clubs, those sorts of things. And now it's morphed into, we're almost 65% in-class implementation with the regular elementary teachers, not the STEM specialist. We do have a lot of librarians that do this in the school, and we do have some gifted and talented, but our big focus is trying to put this in the hands of teachers so that they can use it during the regular class day. So again, this one, the initial cost on the JBC, the actual robot costs $500. We expect the lifespan on it to be about 10 years. And keep in mind, you can run 5 students simultaneously on the same robot. So the interesting thing is the controller itself is not a toy. We use the same robot in the high school and the same robot with the college, even in some postdoc research, it's the same robot. So next slide. So the BotBall program, this is the competition piece, and this was what the organization was founded on. So after Woody Flowers did the mechanical stuff at MIT, in the mechanical lab, the guys on the autonomous side started the 6.207 class, and that's what BotBall sprang out of. So the idea is autonomous robots only controlled by code, no remote control. And the other key idea about BotBall is that it is a level playing field and it's done by students. So adults aren't allowed to work on the robots, adults aren't allowed in the pits. This is not a robot project, it's not a mentorship model. This is not for the old guy who always wanted to work on robots who now is an engineer giving back. This is about kids getting a box of parts and everybody in the world gets the same box of parts and then going to solve an open-ended challenge using 2 autonomous robots to solve it. We do it in a head-to-head competition. Included in the competition, they have to do online documentation, which includes having a GitHub repository to push code. We're teaching them agile techniques for program management, and then they do on-site technical presentations. And then 2 autonomous robots in a pretty complicated game. The game changes every year, a lot like FIRST or VEX or one of those. The only thing is, again, it's kids only, and it's all software controlled. So this one runs 13 US regionals. I think we've got 6 international events currently running with this too. The cost on this one, it's a little pricey. It's $2,500 for the first year's participation, but that includes all the equipment to build 2 robots at least, 2 days of professional development, entry into all tournaments. It's turnkey after that. In subsequent years, schools can reuse part of the equipment and play, all the way down to $1,000 a year. And this one's important because we also have scholarships from NASA, who's one of our biggest sponsors. So NASA usually offsets the cost of at least half or more of that initial cost to get a school going. Next slide, please. And so COVID hit, right? What do you do with a hands-on robotic thing when it's all about hands-on, getting a robot in the hands of a kid? Their eyes light up, they love it, they can see it move, everybody's excited, and then we went virtual. Well, to go virtual, what we had to do was develop a simulator. So what we did is we did 2 things. One, we developed a robot simulator that absolutely mimics the game mats in JBC, which ties to all of the curricular activities in the curriculum. And then we also put a virtual IDE up, or integrated development environment, which is also exactly like the integrated development environment on the robot. So the teachers are using the IDE to manage the class assignments and the kids' code. And the kids are using the robot simulator to simulate what they were doing in person with physical robots. So to date, we've had, well, since COVID hit, we've had about 3,000 students utilizing the simulator. And so we've got some that are straight virtual. All they do now is learn how to code using the curriculum and the simulator and the IDE. And then we've got some that are hybrid. So they use the simulator to practice at home. And then when they come into the school once or twice a week, they run the physical robots. And then we've even got some that are using them in tandem with physical robots that are in school full time now. So the simulator was a real nice addition to keep this going for STEM teachers. And we had a lot of teachers that jumped on that were doing other things because they just canceled their programs. There was nothing they could do. So teachers are still using this to teach code. And I'll be honest, it's just a lot of fun. It's not as great as a physical robot, but it's the next best thing. Okay, next slide. So we too are going to be at Pathfinders this summer. So if you haven't signed up for Pathfinders, this is a fantastic opportunity to take some professional development. People who sign up for our class will get a robot. So we'll actually send a robot out to you. You'll get a year's registration, and we'll do the professional development. We actually break out our professional developments into beginners, intermediate, advanced. We also do units on STEAM. So one of our ball advisors is Dr. Halayenko at UMass Lowell, who piloted, the Robotics that NSF funded years ago, and they did it at the Science Museum of Boston. We've taken all that curriculum and wrote a complete STEAM unit. We've added a package to it for the Steambotics to do kinetic sculpture, and we're adding the circuit package to it. So you're going to have all the wires and LEDs and all that piece that goes with it, because you can use the actual controller to control those. Right. And we've got the libraries written around them. And then we're also teaching the math. So, the math on figuring out, do we need to put some kind of something in this circuit because this particular LED only runs under these specifications, and here's what our current is. How do we do that? So we've got some higher end and even beginning circuitry in there as well, with the goal that, a lot of our kids build inventions and build kinetic sculptures and build those sorts of things. And so that component's added in there as well. And then one last thing, everybody always asks, well, what about a text-based programming language and why C? Well, we like C1 because we've abstracted it out to the level that we have a library, but I like kids to have to be able to make a mistake programming. I think it's important. I think if we make it so easy that they don't make a mistake, so the poor dears will get frustrated, we're doing them a disservice. I think they do much better when they learn the syntax and it doesn't take them long, trust me, and they just start programming. So once they get that down, we've seen transition to fewer edits in the English classroom. We've also had some research come out of Mid-Dell last year that showed improvement, a 1.5-year advancement in math scores in 4th grade girls, simply because of the numeracy and the number lines and the order of operations and the arguments and all those things that that the text-based code actually transitions to. We have added Python, so there's a full Python unit. People want to do Python. We typically, our scope and sequence is 100% of our JBC teams have already done Scratch. They've done it for, a couple years. They're ready to go to a text base in second or third grade, and they just go. By the time we get them in fourth and fifth grade, a lot of those kids are writing their own source files and header files. Once they can do that and they kind of understand how files work, then it's ready to go to Python. And now we can talk about objects and how those kind of things work. So we see a really good transition running in that. Yeah, last slide. So here's our contact information. And again, we're a small organization, but we're very responsive. So there's phone numbers, emails. I've got teachers all during the day that are texting me with I've got an issue, this won't go, or I've got an issue teaching this concept or whatever it is. We'll just sit down wherever we're at and we'll sit down and type or Skype right in with them or Zoom right in and help fix it. So all in all, if you're looking for something physical, and I know it says robots, but now I think you realize it's a whole lot more than robots. It's a robot, it's a complete curriculum package. It's all the PD that goes with it. The activity mats that the robots run on in the classroom are simple, and the game pieces we use are water bottles or soda cans. So this is designed for sustainability. After the first year, the junior volleyball program costs less than $75 a school to keep running. And in some of those schools, like I said, we're reaching 300 kids. So if you're looking for something to add to your computer science program that's got robots in it, but it's not necessarily a competition, go. And I did see the one question, high school teachers. I'll tell you what, the high school teachers during COVID, we took the elementary curriculum, we took all the elementary signs and all the little activities elementary off and gave it to the high school teachers, and they love it. The high school kids, the only difference is they go through the curriculum faster. And the curriculum's such that up on the top end, I mean, there's using OpenCV to do real-time blob tracking. There's really advanced stuff in there, and the high schoolers just go through it a whole lot quicker. So yeah, my answer is yes, you can be a third grade teacher or a high school teacher and still get a lot for your kids out of the program. All right, I think that's about all I have.
Thanks, Steve. And if you have questions for Steve, just a reminder, you can put them in the chat or join the breakout toward the end of the session. Next up, we have Jacqueline from Make Code. You there,
Hey
Jacqueline?
everyone, can you hear me and see me okay?
I can't find you. Where are you? I was going to spotlight you.
Oh.
1 sec.
Can
There
you
you
hear
are.
me, Colleen?
Yes, yes, I'm
Great.
going to spotlight you now. There you go. There you are.
Hi everyone. I have Seattle in the background, although it doesn't look like that today, but but that's where I'm from. It's nice to meet everyone, and thank you, Pauline, for inviting me on the call to speak with you all. My name is Jacqueline Russell. I'm a program manager on the Microsoft Make Code team. So Make Code is a CS education platform for physical computing devices and also games, with both drag and drop block-based code editors, as well as JavaScript and Python text coding editors. And really our mission is to inspire new generations of technology creators. And the hands-on computing tagline here is really a term we use to talk about this idea of combining the creativity of making and sort of the maker mindset with the power of code and computational thinking as a way to help make learning about computers and technology more accessible and interesting to a wider audience of students. I think there's been a lot of research around physical computing and the benefits it brings to broadening participation in computer science. So, so it's a great entry point for many students to computer science and computational thinking. Pauline, would you mind going to the next slide? Great. Okay, so what is Make Code? It's online, it's a web-based tool, it's free, it's an open source product as well. And it's a set of code editors that support various different products. Like I mentioned before, we do have both the drag and drop visual programming interface, as well as JavaScript and Python. And we're really trying to encourage students to use that as a progression path from sort of the visual block-based programming into sort of real world skills using real world programming languages, and also trying to meet learners where they are, right? And with MakeCode, you can switch back and forth between these different modes of programming, and do sort of that two-way editing. So we know that students don't just wake up one day and say, oh, I'm a text-based programmer, so this allows them to sort of, once they start, exploring in, say, JavaScript, they can also fall back into blocks too, if they, if they want to get their bearings and then move forward. So we, like I mentioned it also, we use physical computing and game-based learning as sort of these inclusive approaches to computing education. We really want to make sure that all of the projects that we have are fun, engaging, and relevant to many different student populations, right? Including underrepresented student populations like girls and others. So it's, we really try and make it, coding not for coding's sake, but coding in service of, creating a tower in Minecraft or a magic wand or something like that, right? So these are the products we support today. So we have a code editor for the Microbit, for Circuit Playground Express, for Chibitronics, for the Chibi Chip, for Lego Mindstorms, Q, Wonder Workshop's Q Robots, not listed here. And then also Minecraft and Arcade, which is a game development environment. You can always learn more at our website. If you just go to aka.ms/makecode or just makecode.com, you'll get there too. All right, next slide. Yeah, so I wanted to spend some time just talking about a couple of our physical computing devices. If you could go one previous to this, I think folks have mentioned the Microbit before. This is a great intro product that you can use as young as like 2nd or 3rd grade and all the way up through high school. It's very, very flexible. On the slide is an older version, but I'm holding up the new version of the Microbit, which has speakers and microphones built in as well. So that's, I don't know if you can hear that, but it plays sound and it also hears sound as well. So they've added that as well as a improved processor and things like that. But I just wanted to put this diagram on the slide to show you some of the different sensors that's on here. So it's got some input output rings. It's got a light sensor. It's got those red LED lights that can be used as display to show not just pictures and graphics, but also numbers and letters and words. And then it's also got an accelerometer, which measures motion sensing, a compass or a magnetometer, so it can tell sort of direction and also gravity. And there's tons and tons of accessories for the Microbits. There's all sorts of maker kits, robotics kits, weather stations, just anything you can think of just to plug in to this little device. They're, like I said, very flexible, great onboarding experience into the world of physical computing because there's so much value packed on this little board that's relatively cheap. So yeah, and Colleen just put it in the chat. Katie Henry, who works at the Microbit Educational Foundation, she couldn't be here today, but she has a lot of fun project ideas as well on her website. All right, next slide. So the Circuit Playground Express. So this is another board very similar to the Microbit. I'm just showing it right here too. It's round, so it's not square, but it's made by a company called Adafruit, which are very big in the maker community, in the maker space. And it's similar to the Microbit. It's got a lot of sensors and components packed on one little board here. So including light sensors, a speaker, microphone. It's got these colored NeoPixel lights, which are amazing if you want to do like light projects. Like I've got it hooked up here to a NeoPixel strip. And it's just using the accelerometer to sort of graph the lights based on how far I'm tilting it. But you can make all sorts of fun wearable projects too. In my experience, these are great for like girls' workshops. There's tons of fun stuff you can do with the different colored lights and all the different sensors and stuff. So these are also great intro to physical computing devices that you can use, you know, from, I would say, upper elementary through to high school level. All right, next slide. Okay, and this slide I just put on here, a bunch of resources available for you all. Again, all of these resources are free and open source. So if you want to download this slide deck and just keep these links in your back pocket, there's great tutorials, great curriculum, that's sort of full semester length curriculum, as well as links for where you can buy these physical computing devices and also any accessories for them. All right, next slide. And this is just my last slide. I just want to also let you know, so in addition to the physical computing devices of the Microbit and Circuit Playground Express, we do have a game-based development environment called MakeCode Arcade. It is sort of web-based, so kids will program a game that they can play online on the web. But there is, because we are so focused on physical computing, there is physical devices like this one I'm just holding up right here. So this is a game that I programmed using MakeCode Arcade, and I just downloaded it onto this little kind of handheld Game Boy type device. So there are physical computing parts of this game development environment, totally optional, you know, if you don't need to buy any of the physical stuff, but certainly it makes it a lot more fun, and it makes the students feel like their games are more real and have come alive. There's also, we just came out with a advanced placement computer science principles curriculum for using MakeCode Arcade. And this is a year-length curriculum aligned with the College Board advanced placement exam. And that curriculum is available online. It's free and, again, open source. We are hosting some training around this curriculum this summer at Pathfinders as well, just like everyone else. And the Pathfinder session is free for the first 20 educators who sign up. So if you're interested in teaching CSP using MakeCode Arcade, feel free to sign up for this PD this summer, and we'll go through the whole curriculum. And no background experience is needed. All right, that's all for me.
Thanks, Jacqueline. Just a reminder, Jacqueline is here to answer questions in the chat, and then you can meet with her at the end as well during breakouts. Up next, I gotta switch here. This is a process. I think there's 3 of you here. We got Chibitronics, and here from Chibitronics tonight is Susan, Natalie, and Ivy, I believe.
So, hi, this is Susan. Ivy's going to start us off. Natalie had a class to attend, so it's Ivy and Susan.
All right, let me spotlight both of you.
There's Ivy.
That is me.
And Susan. Oh, no.
Yeah.
You're moving on me. Oh, you turn your camera on.
I just turned it back on.
There we go. Perfect.
Hey. All right. Hello, everyone. I am Ivy Daniels, and I use Chibitronics and help do presentations for Chibitronics. It is just a great little device that, and I'm going to start reading just a little bit from this slide because there's just a lot of great stuff here that I'm going to make sure I don't forget. So Chibitronics makes kits and materials for paper circuits, blending circuit building and coding with art and design. I got to stop right there because that is amazing right there. We have the way it combines just so many things to take that science, that electronics, and that circuit building, and then combine it with art and programming. And there's just so much for students to do. And so I really wanted to highlight that, just the fact that there is that circuit building and the coding and the art, and all of it just works so well together. It's a friendly way to learn design and create your own electronics using familiar and beautiful creative materials. I have to tell you, I use this in my class. And the reason why I, present with Chibitronics is because I use it in my class. And I see how there's something for so many of my students. Pretty much everyone can find something they like about Chibitronics. You have those kids who are really into the design portion of it. You have those kids who are into the electronics part of it. You have those kids who are into coding, and they all get to work with their hands, and they all get to personalize something that's really personal to them. Like normally I do projects with my students all the time. And at the end, when it's time to give back their projects, I find them shoved in the desk, they're floating on the floor. Some other teachers bringing it back to my classroom because they've left it in some other class. I don't have that when they do the Chibitronics. They want their projects. They love, they work hard, but they love what they've come up with at the end. And they want to take that with them. And they are just so impressed. And there are times when I'll say, okay, here's where you can get, your own. And they're all, we normally very interested in, how do I get my own? How do I do this outside of the school building? So your students are absolutely going to love working with the Chibitronics. And you as a teacher are also going to love working with the Chibitronics. Chibitronics team is so accommodating. They will bend over backward to make sure that you have what you need as far as professional development and helping you come up with lesson plans, or showing you lesson plans that we already have, and videos that are out there to help you in any way that you need. So that is another reason why I really love working with this team, is that I come up with some crazy things. Natalie, who's not here right now, I called her just today and said, Natalie, I have a great idea. My students need to use the restroom, but we can only have a few students in the restroom at one time. How can I use Chibitronics to make a visual representation of, hey, somebody's in this bathroom? And so they could see the light, and say, oh, somebody's in the bathroom. I have to wait until they come out. Now, it's still something that, we're looking at, and we don't have all the kinks worked out. But the fact that Natalie took my phone call and said, you know what, we'll look into this. And I think it could be done, and let's maybe make this into a challenge for the students. And she reminded me that, Ivy, you don't have to think of all the answers and have it all figured out for the kids. Let's make this into a challenge for the students. So I know Susan's probably looking at me like I'm going overboard with the Chibitronics stuff, but I have to tell you, it really is fantastic to be able to have your students work in so many modes. Like I said, we have that science, we have the art, we have computer science, and you can start with kids as early as elementary, lower elementary. And you can work I teach middle school, and I use it, and you could work with kids who are in high school, and you really just start the kids where they are. If you want to talk more about circuits and how those circuits are built, you can do that if you're the science teacher and you want to incorporate that. If you want to get more into the programming, you can do that. If you want to, if you're that art teacher or want to work with the art teacher, again, you're starting kids where they are and saying, okay, what do you want to do? And having them move. I'm sorry.
Ivy, no, it's okay. We do have to go on, but Ivy, talk about the picture of the little beach scene with the lights. How was that made? Can you sort of take that apart?
Take this apart.
Do you know what so all right, let me not put you on the spot because you didn't develop this. So what this is a beach scene in this little picture on the slide, and in the water are iridescent fish that you can see are all lit up, and because it's hooked up to a light sensor, you can put your hand over the sensor, and as your hand gets closer, you can't see the fish anymore, but the house lights come on, and then you don't see them in this picture, but there are street lights behind it. The street lights come on, and then ultimately the stars come on in the back. This was a project done in the winter 2020 Pathfinders, when we actually could all gather together. So this was a team of like 7 teachers that did this in a 3-day workshop, starting with some of them had no background in circuitry or coding, and they just took to it like duck to water. It's great. So that you can see in the picture on the left, the chibi chip that was mentioned. Yeah, sorry, I forget your name. Yeah.
Me?
No, Jacqueline mentioned the chibi chip for the make code. You can see that it's just a clip that clips onto the paper, and you bring the circuit made out of the copper foil that has sticky on the back, and then you can program actions with the lights. But really what I want to do is go to the next slide, if you don't mind, and play that video. This is the person that is our wonderful creator, and yeah, she's awesome. Can you play that? Will it play? So if you can make it full screen, that would be awesome. And what you're seeing is a humongous piece of butcher block paper with the India ink painted on the top of the paper. And behind the paper are all of the little LED lights that have been programmed to turn on and off in a physical computing way. And the microcontrollers are, in this case, they're soldered to the circuits, the copper tape circuits. There is a little microphone that picks up the wind, or you'll see the wind come in just a minute when G comes up and blows on that little dandelion video. Yeah, dandelion puffball. So this is actually interactive artwork that when I saw this, all I could think of is I need to figure out how to take this to my students. And I began working on figuring out how to write lesson plans and get all of the hardware I needed. And in the meantime, they were developing this chibi chip piece, and it allowed me to take it down to 3rd and 4th grade, so that because I didn't have to solder microcontrollers onto anything, just use the chip. So basically you're seeing the metropolis of copper tape, and inside the little circles of copper are the microphones, and down below are the microcontrollers soldered. And what she developed was a little LED that is on a sticker, and it has a I can never remember the word, but you know what it is, resistor. It has a resistor in it already, so yeah, there's some science in there that I don't need to explain, but it's the resistor really helps. So basically, this was part of a project, and she's going to talk about this, I hope, in just a second. Oh, I wish I had control of this because I would take this ahead. I know we don't have time. Do I? No, I don't.
Blend craft with technology.
Oh, here we
This
go.
all came out of my PhD research at the MIT Media Lab, where I explored ways to blend traditional art media with electronics and programming. And the idea was to see how we might express ourselves differently through creating these new types of technologies with this new media. And another goal of mine was to see how can we use traditional and friendly materials like paper, conductive paints, to engage more diverse audiences in creating their own technologies. To this end, we've created circuit stickers, which are flexible printed circuit boards that look and feel like stickers, but behave like electronic modules. And by building these circuits on paper, you still have all of the expressive and aesthetic affordances of the traditional paper medium. In working with educators, I've learned that it's important not only to make the tools, but also create the support resources. So I wrote the circuit sticker sketchbook. The idea is that you build the circuit on one page and you turn the page to find a drawing. And
Cool,
so
Ivy.
every activity is both a blend of engineering and art. Our readers not only think about how to build a circuit, but they also think about what are they making and why are they making it, creating something that's meaningful and personal to them, so that it's not an abstract exercise. After learning basic circuitry, we created a new book called the Love to Code book to introduce more advanced electronics and programming concepts. Along with this book, we actually made a powered binder and a programmable clip that is specifically made to integrate electronics with paper. As with our previous book, we coupled every activity with both circuit building and programming along with art making. By adding code to their projects, readers can now do more advanced things like making lights flash or integrating sensors to make their works interactive. We developed our own programming interface that runs online, so there's no need to download any software. It runs Arduino for those who know how to code. We also have a Scratch-based block programming language that was developed in collaboration with Microsoft for younger users. Everything can run on a phone or a tablet, so you don't need a computer, and code can be uploaded through anything that can play sound. So even an MP3 player can be used to program the chip. Everything we create is under Creative Commons or open source licenses, with the hope to make our work as accessible as possible and to invite people to not only use our tools, but also remix them and design their own tools. Since first launching Chibitronics in 2014, we have reached artists, educators, designers from all over the world and seen all sorts of different creations, from light up poetry to decorative greeting cards to all sorts of artwork. One thing that really inspires us is seeing how so many people who didn't think they were capable of creating their own technologies absolutely can. My hope is that one day we will think of circuitry and programming as yet another expressive medium, something that anyone can use to turn what's in their minds into something real, and to think of technology as something that we don't just consume, but design and make ourselves, for ourselves, and for those around us. A simple example of a paper electronic circuit is this pressure sensor. So there's your battery, that's your power supply. We have copper tape to act as the wires. There's two red LEDs and then one little handcrafted pressure sensor. The harder you press, the brighter the light. Very simple. And that's the electronics portion, but you add a little drawing and it completely changes things. So here's a character. When you give him some love, he blushes and loves you back. And it's just a drawing, but you can see when you combine these two together, the drawing comes to life, the circuitry takes on this whole nother layer of meaning. Writing and circuit making are both ways to make marks on paper. They're ways to communicate your ideas. They're even ways to think about ideas to yourself. Because a lot of educators, for example, they start off with the stickers, for example, but then they move on to bare microcontrollers. They move on to smaller LEDs because they're actually smaller and integrate better. So I've seen that. I've seen an English teacher who never did anything with electronics, but then got really into it and then joined his local makerspace, and now he teaches a programming class at his school in addition to his English writing class. Some of the crafters were just so far happy with using kind of a set of circuits, but then taking it in all these crazy directions through the artwork. Well, one thing that came to my mind was like, look, if now suddenly, by the way, many of the bloggers that have shared their work are definitely mothers, because they talk about their kids, they make things for their kids. What if now you see both dad building electronics and mom building electronics, having that kind of role model, I think will change.
So here, she gets very emotional right here.
Hung out with his dad building electronics as a kid, and mom was in the kitchen. It's a great world.
So that's the end of the video. This is part of and if you can go to the next slide, please. Yes. So this is a collection of videos that are on YouTube that kind of delve into a lot of what we've done so far, from Natalie talking about professional development to Barbara talking about the art well, part of this was from the National National Art Educators Association. We put some of this together for them as well. And then I talk about how we built the program in schools. And then Ivy talks about a lot of what we've used. There's so many things that everybody else has said that kind of works in with what we've done, and we've been going on a long time, but the professional development opportunities include, like everyone else has said, the Pathfinders, where we're going to be building paper cities. That's just because I really like that. There's so many other ways to do that, but the paper city actually does give you the ability to take computer science across across all curriculum, from English language arts to social studies. Ivy doesn't even know this yet, but I think we're gonna be focusing on space travel with this. So one of the pieces is we're going to make maybe not everybody, but Ivy and me, and then the teachers are going to be creating a moon city, and then yeah, there you go. And maybe your students can make yours, Ivy. You don't have to actually do it. And also one on Mars. We've got so much really cool stuff to offer the teachers that come. But we are also, in addition to Pathfinders, we are starting to teach through Eventbrite. So if you have this presentation, you can click on there and get the links to that. Last slide, please. I think it's the last slide. Oh, I thought we had another slide. I guess we don't. So we're good. Oh, there it is. So this just breaks down, yeah, that just broke down the levels that we're actually doing 3 levels at Pathfinders and through Eventbrite, where we have tried to throw everything at the teachers to learn everything, and it doesn't work very well. So we are going to start just with the circuitry in level 1, and then programming and computational thinking with the Chibi chip microcontroller, and bringing in all kinds of, well, you can see conditional statements, loops, events, and multi-threading. And then level 3, we are bringing in motors and yeah, 3D construction and some really fun things. So that's it. That's Chibitronics. There's a lot more. If you go to chibitronics.com, you can see all of the support that G has made available to everybody, that just what Ivy was talking about, that they have made it very easy to teach our children. Yes, that's it. Thank you for having us, everybody. And, see you soon.
Thanks, Susan and Ivy. If you have questions about Chibitronics, you can feel free to hold on to those just a moment, because we're going to go into some breakout rooms. These are not required. These are optional. And let's see if I can do this. Alexis, are you still there for me?
I am.
Can you assist me with setting up the breakout rooms
Yes.
by provider?
Give me just a minute.
Yes.
All right, so we can have them go just in order.
So
Makey in room 1, KIPR in room 2, Make Code in room 3, and Chibitronics in room 4.
Thank you.
thank you to all of our presenters as well.